Hey folks, welcome back uh, to our new format, all online. It's new to me, so let me know what you think. We're going to go through and make this as painless as possible. Um, I've put up on the board uh, some information that I'm sure that we went through um, before the break started, but I figured we might as well recap on this and let you know the important things. This is in Chapter 8, okay? Um, Chapter 8 is about static equilibrium. So up here in the top corner, I've got the name of the chapter, Static Equilibrium, and there's two conditions that need to be met when a system is in static equilibrium. The sum of the forces acting on it must be zero, and if the sum of the forces are zero, then Newton's laws tell us that the acceleration of the system will be zero. Its speed will not be changing. In a lot of cases, it means that the object will not be in motion at all if it starts with no motion. Okay? The other criteria that's super important is that the sum of the torques acting on the system, the sum of the torques must be equal to zero. If the sum of the torques is zero, that means that the spin rate of the object can't be changing. Okay, so, and typically, in a lot of cases, that means that the object, which, if it starts with no rotation, then it won't rotate, okay? And you think about civil engineering, it's all about building objects that are in static equilibrium. You don't want to walk into a building that is either accelerating or changing its rotation rate, right? Okay, so these two criteria must be met for an object in static equilibrium. Here's the definition of torque. Torque is equal to the force acting on an object times the distance from the center of rotation of the object to where the force is being applied times the sine of the angle between the radial vector that points from the center of rotation out to where this force is being applied and the direction of the force itself. So we've talked about this definition of torque, and we've used torque previously in a different chapter. So now we're applying it to the static equilibrium condition. So I believe I did this example on the board for you before. Here's somebody walking across a footbridge, and what we want to do is find the forces acting at the support ends of the bridge. Support force A is pressing upward at pylon A on the left-hand side of the bridge. Support force B is pressing upward due to pylon B acting on the right-hand side of the bridge. We've got somebody walking across the bridge. He's 2 meters from side B. As he's walking across, he has a weight of 500 newtons. The weight of the bridge itself acting at the center of the bridge is 1,000 newtons, and the length of the bridge is 10 meters. Okay, so we want to solve for force A and force B. What are they going to be equal to? Well, we're going to use these two criteria for static equilibrium to solve and determine what FA and FB are. So if we sum the forces acting on the bridge, well, there's force A acting upward, force B acting upward, and then we subtract from that the total force acting downward, which would be the 1,000 newtons of the weight of the bridge itself and the 500 newtons of the person walking across the bridge, so that's minus 1,500 newtons, and that has to be equal to zero if the bridge is not accelerating. Okay, so that's the first criteria in static equilibrium. The second criteria, the sum of the torques must be equal to zero as well. Okay, now whenever you're summing torques, you have to choose a point of rotation. Even if there's no rotation in the object, you choose a point of rotation, or you can't define the radial vector, the distance of the radial vector, which always points from the center of rotation to where the force is being applied. So in our case, we're summing the torques at point A, so I put a little curly arrow that shows that that's what I consider to be the rotation point for the purpose of summing torques. And now support force A cannot exert a torque at point A because it's got a zero distance, so the radial vector is zero. So no torque due to force A. However, the weight of the bridge is trying to make the whole bridge rotate in the clockwise sense at point A. Okay, so the weight of the bridge is acting perpendicular with respect to the bridge with a force of 1,000 newtons. So here's the force. Remember, it's force times distance times the sine of the angle between those two vectors. So it's 1,000 newtons the weight of the bridge. Then the distance that that force acts from the center of rotation, which is A, is half the length of the bridge, so that would be 5 meters, okay? And since the radial vector points from the center of rotation out to where the force is applied, it is horizontal, but the force itself is vertical, so the angle between them, the angle that would go here if we were putting this angle in, would be 90 degrees, and the sine of 90 degrees is 1, so I'm not bothering writing sine 90. It's just 1. So 5,000 newtons times 5 meters is 5,000 newton meters, and that is the torque exerted at point A due to the weight of the bridge itself. Now we add to that the torque due to the man walking across the bridge. Well, his weight is 500 newtons. His distance is 8 meters, right? 10 meters minus the 2 meters that he's already traveled across the bridge. And the sine of 90 is still 1 here, so 500 newtons times 8 meters gives you 4,000 newton meters, which is the torque exerted by the man on the bridge at point A. Okay, now we've got the negative of another force, okay? Support force B is trying to push upward, well, it's pushing upward on the right-hand side of the bridge, trying to cause, well, it's exerting a torque that would, if it could, cause the whole system to rotate counterclockwise, since the negative sign in front of it compared with the positive signs in front of the torques due to the weight of the bridge and the weight of the man himself. Okay, so, and then its distance from point A is 10 meters. So we set all of those summed torques equal to 0. We've summed all the torques, we set them equal to 0. Now we've done everything required for the second criteria to be met. Okay, so 5,000 newton meters plus 4,000 newton meters is 9,000 newton meters. If we divide through by 10, we get the support force B isolated is 9,000 newton meters divided by 10 meters, which is 9,000 newtons. And if you plug in 9,000 newtons right here and subtract it from both sides, you can solve for support force A, which is 600 newtons. So that's an example problem using the two criteria required for static equilibrium. We'll do some more problems in a different video. I'm going to keep these individual videos kind of short to save memory space on my phone. I'm using my phone. So that's good. And that covers most of Section 1 and Section 2 in Chapter 8. Section 3 in Chapter 8 has to do with Hooke's Law. And we've talked about Hooke's Law before, but I'll include that information here as well. I'm going to erase this board. And include the information about Hooke's Law. Hooke's Law has to do with elasticity. Elasticity is the ability of an object to be stressed and deformed from its original geometry, and upon the removal of that force, whatever force caused the deformation in the object goes back to its original shape. So something that's more elastic can be stretched to a greater extent, and upon being released go back to its original size, compared with something that's less elastic, which can just be stretched a little bit before it breaks or becomes unelastic. So Hooke's Law has to do with springs. let's see, here I'm going to draw a picture of a spring hanging from a ceiling. Okay, now this spring has no weight on it. We consider it to be massless, so it's just hanging at its natural unstretched length. On the other hand, okay, we're going to take that same spring now and hang a weight from it. Okay, with a mass M. Okay, now that we've done that, we have stretched it a certain distance. Call that delta x. Okay, that's a displacement, so we call it a vector. All right, now there are forces acting on this. Now what we've done is we've hung this mass from the spring and just gently let it go down to its new length. Okay, it's been stretched, so it's got a new length, and if we draw all the forces acting on this mass hanging at the end, you're going to have an upward force due to the spring itself, which we're going to call Fs, and it's got a direction. It's a force, so it's a vector. And then we've got a downward force, mg. Okay, we can call that a vector too. Okay, now since this object is not accelerating, it's just sitting there, then if we sum the forces acting on it, those forces must add up to 0, right? There's no acceleration, so that means that Fs plus mg, these vectors must be equal to 0. Sum of the forces is equal to 0 because there's no acceleration. So that means that the spring force vector is equal to the negative of the weight vector, right? But these two forces are the same because there must be equal forces in opposite directions acting, or it would be accelerating. So let's just get rid of the vector nature of this, and what the negative sign tells you is that the weight vector is acting in the opposite direction of the spring force vector. So we know that much, and we're going to come back to that information. Here's what Hooke's law tells you. Hooke's law tells you that the spring force is equal to the negative of some constant, which we're going to call K, the spring constant, times delta x. Okay? This Fs, since I didn't draw a force or a arrow over the top, we're just considering that to be the magnitude of this vector, just the size of the force, the number of newtons of force exerted, and delta x, that's a displacement from the natural length. Okay? So delta x, also, we've taken away the vector sign, so we're not concerned with the direction. But we've taken into account, this negative sign takes into account that this vector and this vector always point in the opposing directions. So if you pull a spring this way, the spring force is trying to pull back to the original position. If you compress the spring this way, the spring force will push in the opposing direction. So always this vector and this vector are opposing each other, pointing in opposite directions. That's why the negative sign in Hooke's law. And K is the spring constant. And it's a measure of the stiffness of the spring. Or the strength of the spring. it's measured in units. Now, if you divide through by delta x, you can isolate k. Don't worry about the negative sign here. Remembering the negative sign just tells you that these two vectors point in opposing directions. So k is going to be the spring force over the amount of compression or stretch or deformation from the original length. Okay, so the units for spring constant are newtons per meter. Which makes sense if you think about it. You know, how much force per unit length is required to stretch this particular spring. If it's a really hard spring to stretch or compress, it's got a very high value of K. If it's a really easy spring to stretch and compress, it's got a very small value of K. So that's Hooke's law. And that's a good place to stop. That's really the material that's important in chapter 8, section 1, 2, and 3. So I'm gonna call it quits here, and I will pick up with another video just in a few minutes.